When we graph a line, we create three disjointed subsets: the line, the points above the line, and the points below the line. If points on one side of the line will satisfy an inequality, the coordinates of all the points on the same side of the line will satisfy the same inequality. The line that we have graphed here is y is equal to negative 1/2 x plus 1. We want to determine if the points above the line correspond to y is greater than negative 1/2 x plus 1. To determine if those points correspond to the inequality, we'll take each one of them and sub them into the inequality just to show that if one point proves true, that all the points will prove true. So we took negative 2 and 4. We subbed that in. We found that 4 is greater than 2, so that statement is true. We subbed in 4 and 5, and we found that 5 is greater than negative 1, so that's true. And then when we subbed in 5 and 2, we found 2 is greater than negative 3/2, which is also a true statement. That tells us that indeed all of the points above the line give us the value of the inequality y is greater than negative 1/2 x plus 1. So if we could prove that the points above the line are greater than the value of the line, then we should be able to prove that the points below the line are less than. So we reverse the inequality, we pick a point below the line, in this case the origin, and we sub it in for x and y. The origin is 0, 0, and indeed that statement is also true. So that tells us that points above a line are greater than and points below a line are less than. The line itself is equal. If we look at this inequality statement, we see that y is less than or equal to 1/3 x plus 2. And a look at the corresponding graph shows us that we have a solid line, and then we have the shaded part that represents what's less than the line. Now in this inequality, we have y is less than 1/3 x plus 2. And if you notice, we have the same part shaded, but our line is dotted. When we don't have the equal to on the less than or greater than, the line is not included in that inequality, so we have to make that line dotted to show that those values are not included in the equation. If two linear equations are not equivalent equations, then the lines designated by them either intersect or are parallel. Lines that intersect create 4 distinct areas on the plane. Lines that are parallel create 3. Here we see a graph with two intersecting lines, and we see the areas created here. We have area A, which is above both of the lines, both the green and the red. Area B is below the green line but above the red line. Area C is above the green line but below the red line, and Area D is below both lines. So let's take a moment to evaluate the graph that we have. Both of the lines written are solid lines, so they're equal to. So our areas around these two intersecting lines are all going to be less than or equal to or greater than or equal to. Area A is above both of the lines, so it's going to be greater than or equal to both of the lines indicated. Area B, on the other hand, is below the green line and above the red line, so it's going to be greater than or equal to the red line, but less than or equal to the green line. Area C, on the other hand, is below the red line and above the green line, so it's going to be less than the red line, less than or equal to, and it's going to be greater than or equal to the green line because of where it's located. D is below both of the lines, so D is going to be less than or equal to both of those lines because the lines are solid and they are included in this inequality. Here we have another pair of lines that are graphed, but these lines are parallel, and you can tell that they're parallel because the slope is exactly the same. And if you look at their plus b or their y-intercept, that is going to tell you where they're located. Even though they're parallel, it can tell you how far apart they are on the graph. So note that area E is above both the red and green lines. F is between the red and green, so there it's between the two lines, below the red and above the green. And G is below the green, so it's below both of the lines. So let's look at the areas defined by the parallel lines on this graph. We have our red line, and then we have our green line, and both of them are solid lines, so all of our inequality statements are going to have an equal to component. The first area is area E, and it is the area above both of the lines. So because of that, those inequality statements are going to be greater than or equal to. Now, in between the two lines, we're going to have a section that is less than the red line, less than or equal to, but then we also have greater than or equal to the green line because we have points above that. Now, area G, both of those lines are above that area. So area G is below both of the lines. So it is going to be defined as being less than or equal to both the red and the green line. Now keep in mind when evaluating these equations with a set of points that the set of points has to be true for both of these conditions in order for it to be included or considered as true for that area. And what I mean by that is if it is less than the red line but above the green line, it will not be in section G. It would be in section F. So both of those conditions have to be met. In example 1, we are going to graph the solution to these two inequality statements. So in order to graph them, we're going to set them equal and make them linear equations. So y equals 1/2 x plus 2 is the one that we have graphed here. But because our inequality is less than but not less than or equal to, it's going to be a dotted line. Our second inequality is y is greater than or equal to negative x minus 3. The line that is graphed is y is equal to negative x minus 3. Now we're going to shade in the area that proves true for both of these inequality statements. And since we're looking for less than the first line, it'll be below, and greater than or equal to the second line, it'll be above, and that gives us that section on the right-hand side between the two lines where both of those conditions are met. In example 2, we're going to graph the solution to these two inequality statements. Now these are parallel lines, we can tell because the slope is exactly the same for each one. It's 1/1 for both of these. Now the first line that we're going to graph, we set it equal, y equals x minus 2. So the first line that we graph is the dotted line. The second line is going to be a solid line because it is less than or equal to x plus 1. Now notice the inequalities here. We have y is greater than the x plus 2 or the dotted line, so it's going to be above that line, but it also has to be less than or equal to x plus 1, so it's going to be below the solid line. So that gives us the section in the middle. Those point to the ones that will satisfy both of those inequality statements. Let's review. Linear inequalities that are less than or greater than are dotted lines, where linear equalities that are less than or equal to or greater than or equal to are solid lines because of the equal to component. Linear inequalities that are greater than or equal to are the points above a line. Linear inequalities that are less than or equal to are the points below a line. Matching slopes indicate parallel lines. Slopes that do not match intersect. As always, thanks for joining us here at Jupiter Math. For more information about our math programs, contact learning@edugraphics.com.